Okay, so welcome back to the WJAC recap and in this episode we're going to be covering Unit 4.5, which is carboxylic acids and their derivatives. So this is part of the organic spec, and we'll be covering the whole course in this episode. It's a slightly longer topic, but we'll cover it all. Okay, so first of all, we're going to start off with carboxylic acids and why they're called acids. So there must be a reason for this. So as I got here is the equation for the partial dissociation of a carboxylic acid. So as it's partially dissociated and it's in equilibrium, it is a weak acid. Still an acid though. Okay, so let's look a bit more at this structure here because you can write it as this and there's another format as well. So as you can see from this, we know it's an acid because if you look at it in the Lewis way, this oxygen has accepted a pair of electrons, or if you look at the Arrhenius way, it is also given away a proton donor. Okay, so once this proton's been donated, we can write this part here in a bit of a different way. Okay, so if we do just any chain length connected to our carboxylic acid, and we'll do it with the O first, and then I'll draw the bond. So this is going to be the electron of the oxygen in the bond, and we're going to do the bond to the hydrogen. This is the electron of the hydrogen. And I'm going to draw in the lone pairs for the oxygen. Oxygen has two lone pairs. Okay. So as we know, to make an acid acidic, it has to be put in an aqueous solution. So in this case, water. So let me draw in our water molecule. I'll draw in the lone pairs. Okay. So now we have our water molecule, and this is going to interact with this hydrogen here, because this oxygen, being electronegative, it wants that electron from the hydrogen. So we're going to move that electron towards there. And then these lone pairs here from the oxygen are going to go towards our hydrogen. Okay. So now from this, we're going to have our carboxylic acid formed. This negative charge, because it's gained another electron, as we can count the pairs. 1, 2, 3, 4. We've got 2 in here, 5, 6, 7. A normal oxygen has 6. So in this case, we got 7. So it's going to be O minus. Okay. And here we'll have our hydronium ion. I hope I said that right. And then so no need for all the electrons. We still have one lone pair on the oxygen. Okay. So now if we look at this specifically here, this is a carboxylate ion. And this negative charge here, the electrons in fact are going to move towards. So we've got an electron here. It's banded on this side, and of course the carbon ones here. And this electron is actually going to go towards this carbon. And then from here, we're going to move these electrons towards here. So then if you draw this further down, we got R, C. I'm actually going to break that bond, but we're going to form a double bond down here. And this process will keep happening. This electron will then move towards there, and we get the same process once again. So we can actually draw this as it's a resonant structure at this point, like this. And this is what stabilizes the molecule. This is what makes it stable, more stable than just your normal alcohol, which has your normal OH group. So like we looked at a phenoxide ion. We've got this complete resonant here. Yes, the p overlap will overlap with this, as we saw with the pi electrons, but not in the benzene step. This makes it more stable. And if you look in terms of its acidity with other things, we can put some numbers with this as well. So a carboxylic acid, pH, is around 2.9, which is then more acidic than a phenol, which is around 5.5. We'll put water into the reference, which we all know is to be 7. And ethanol, which is our example of an alcohol, is approximately 7.9. Okay, so we can test for carboxylic acid by reacting it with sodium carbonate, Na2CO3, and this reaction will give CO2 bubbles and effervescence. So that could be your test, as we discussed, to distinguish between that and a phenol, for example. So to prepare a carboxylic acid, we did before, I'll cover it again, oxidation. But I don't think I covered the colours before, but you can, with the oxidation of a primary alcohol, you can oxidize it to an aldehyde, and then further on to a carboxylic acid. And this can be done with acidified potassium dichromate. And you're going to get a colour change from your orange potassium dichromate, which is actually chromium 6+, to a green colour. And this green colour, as you may or may not have done yet in D block, is Cr3+, which is a green colour in solution. So that's the preparation of a carboxylic acid from a primary alcohol. We also need to know how to form an aromatic carboxylic acid when it's got side chains of maybe an alcohol, so like your phenol, or your aldehyde groups that could be attached. So from this, you have to oxidize them, and this is when the group has to be directly attached to the benzene ring. So if I draw it, for example, that's horrendous. I draw a aldehyde group directly onto the I'll draw it up onto the benzene ring. You can either use acidified potassium dichromate and you get the same colour, change the result for, but most commonly you'll use acidified potassium manganate. It's a stronger oxidizing agent and this will be more stable. Okay, but you can also oxidize an alkyl side chain, such as maybe methyl benzene or ethyl propyl. So I'll just draw a simple methyl group onto it, and this is going to go to getting better. Our carboxylic acid. Now to do this, you're going to have to use an alkali potassium manganate solution. But the problem with this is it's going to form, because it's actually in fact KMnO4, which you use. It's going to form your potassium salt of your benzene carboxylic acid. So it was going to look something like this to start off with. O minus, K plus. And that would be your potassium salt of your benzene carboxylic acid. But to get rid of this, you'd simply just add an acid. So if you add HCl to reprotonate the solution in order to reprotonate this and put a H there and to get rid of that, and you'll form potassium chloride. And it's good to know that it does not matter what alkyl side chain is attached to it, you'll always form a benzoic acid or benzene carboxylic acid. So whether this could have been C2H5, you will still form your benzene carboxylic acid. Okay. Now we're going to move on a bit further onto the production of a carboxylic acid. Now we know two reducing agents. We can use our NaBH4 or LiAlH4. Now, oh, it's horrendous. Now, for this reaction, due to the stability of our benzene carboxylic acid, this can't be used It's too weak of a reducing agent. So we're going to use this one. But it's handy to note that with the carboxylic acid, when you reduce it, you do not form your aldehyde. You go straight to your primary alcohol. It's a one-stop shop, so in this case, it's going to be in respect to 4 hydrogens. Added to get back to your alcohol and your form of water. So it's handy to know with this reducing agent, you can't use your normal aqueous solution of water. You'd have to dissolve it in an organic solvent like ethoxyethane, which is an anhydrous solution, meaning it's got no water. Okay, so now we're going to go on to decarboxylation of a carboxylic acid. Now this is the removal of one less carbon in its chain. It's the removal of CO2. So Now this works as we'll see. So our reagent is soda lime, which is calcium oxide. So soda lime, which is calcium oxide, and sodium hydroxide. Now, as you may or may not know, carbon dioxide is actually an acidic gas. So if you mix acid with alkali, you get salt and water. Classic reaction. So that's how it will work. Or, without the use of soda lime, you can do decarboxylation if you've also already got the calcium salt of an acid and CO2 is removed. And it'll produce, however, that will produce a ketone. Now you do this by heating it. So if you have the calcium salt or the carboxylic acid, like so, you heat that and you produce a ketone, but the ketone has a longer chain length. Oh, Alexa, off. I don't know what happened then. Okay, so that is decarboxylation. So now we're going to do the formation of esters, which we've already covered before. So the formation of an ester from carboxylic acid, we know we need the catalyst of sulfuric acid, concentrated. Concentrated sulfuric acid. And we need to know a bit about which OH bond is broken, which OH lost, which hydrogen's lost, and such. We also need to know it's a condensation reaction, like we did before, an addition, elimination. This is the loss of a small molecule, and in this case, with the normal carboxylic acid, that's water. So if we look at our carboxylic acid, so if I do something like methanol, and the ethanoic acid, we need to know which OH is taken to produce a small molecule of our water. So no water is produced. But where does this H2 and this O come from? Okay. So the OH from the carboxylic acid is the one that's lost. And we lose the H then, obviously, from here. Oh. Now they discovered this by an experiment with oxygen 18, and they were able, so they put in a radioactive isotope of oxygen 18 to decide which one was lost, and they saw that the sample that was lost, the water sample that was produced, was from the carboxylic acid, was the one with the radioactive substance. We also need to just note that this can form equilibrium. So your ester formation might be, your product might be your yield won't be very strong. And that'll be methyl ethanoate formed. We also need to know about acid chlorides. So this is a derivative of carboxylic acid, and you usually write them like this. And these tend to be more reactive, or they are more reactive due to this polarity here. It's a bit weaker than the polarity between the C to O, which is more electronegative than chlorine. So this bond is actually a bit stronger. Hence this, why your normal carboxylic acid is a bit more stable than your acid chloride. So this will do the same reaction as a carboxylic acid would with a normal alcohol. However, there's no catalyst required due to the reactivity of it. This needs to be anhydrous because this is very reactive and will react with water. But your condensation reaction, as you usually produce water, you actually produce HCl, and you'll still produce your methyl ethanoate. It's really messy. Okay, so moving on a bit more. We know it's a condensation reaction. It may know in biology the two reactions you need to do for AS with hydrolysis and condensation. So now we're going to look at the hydrolysis of an ester, which is the addition of water. So this can be done by either like an acid route or a alkali route. The alkali route is better, but we're going to look at the acid route acid route first. So the acid route is worse yield-wise because it actually forms a equilibrium. So I'll do the hydrolysis of methyl ethanoate, and we're going to use dilute H2SO4 and reflux it. Okay, so there's our methanoate plus our water because it's a hydrolysis reaction, and our H plus, which is from our H2SO4, right there. And we will form our ethanoic acid. And our methanol again. So it's the worst solution in terms of yield-wise because of this equilibrium, and it will shift further to the left than the right. However, if we do OH minus hydrolysis, this route, it's non-reversible, so the yield is better. I need to heat it under reflux as so again. So the catalyst we're going to use is a strong base, so we're going to use sodium hydroxide. And there's a few more steps to this route. So methyl ethanoate, and water, and then using our OH minus catalyst from the NaOH, we're going to form our methanol and ethanoic acid. This ethanoic acid will then react with the NaOH because it's in excess, and this will form sodium ethanoate. I won't be lazy, I'll draw it. Just looks something like this. And water, of course. However, this can be easily rectified. You just got to acidify the solution with an acid, so use HCl or even H2SO4 again, a strong acid, to reprotonate it, and you'll get rid of the Na+, and you'll reprotonate with the hydrogen, forming your ethanoic acid again. Right, so now we need to look at the acid chloride reactivity. So acid chlorides are very reactive because they're susceptible to nucleophilic attack. So as we know, a nucleophile can be drawn like this, and this is due to the carbonyl carbon. So it's just this whole polarity business again. cis nucleophile can attack here, and we get the same sort of thing going on again. And this will just leave the product of HCl. So let's say you had OH minus as your nucleophile. This is going to attach into there, and you'll just form your carboxylic acid again. This is by reactions that have to be done anhydrous with it. You could also use maybe nucleophiles, water, you could use alcohols, you could use ammonia or an amine, but we won't look at them. So now we look at nitriles. So nitriles are derivatives of carboxylic acids. We also need to look at amines and amides. These are all derivatives of carboxylic acids. So first we're going to do nitrile. The first reaction we're going to look at is a nitrile, which we know to be a C triple bond N and then R. And this is going to go to an amine. Now an amine is when you've got an NH2 group attached to R, like so. So you can reduce a nitrile to an amine. I'll look at primary amines. This would be a primary amine, for example. So nitrile to a primary amine, you have to use LiAlH4 again, our reducing agent. And because this is strong, it has to be dissolved, of course, in ethoxyethane. And that is the simple reaction of a nitrile to a primary amine. Or you can use sodium metal, so sodium solid, and this has to be dissolved in ethanol, so ethanol. And this will, however, this will produce a primary and secondary amine. So in terms of wanting a primary amine, this reaction is less useful because you get side products produced. You could also use H2 and a nickel catalyst. So this is just your normal hydrogenation kind of reaction. Method 1 is better because you get the better yield of your primary amine, of course. Okay, so now we're going to look at the formation of an amide. So an amide is where you've got C double bond O to an NH2. That is your amide. And of course, I'll have an R group. So the first way you can form an amide is by reacting a carboxylic acid with basic ammonia in H3. So ammonia in aqueous solution is loosely, I think loosely isn't the right word, but it's basic or alkali because you've got this. And we know ammonia is in group 7. 1, 2, 3, 4, 5 also electrons. Okay. So now the second way, and this will this will then result in ammonia carboxylic salt, but we've got to just heat the salt, and this removes the H2O. So this, going back to why this acts as a base is because they can donate these pair of electrons. And we know in the Lewis sense that a base or an alkali is a electron donor or a proton acceptor in the Arrhenius sense. So this is going to produce, when we react these together, it's going to produce an ammonium, which is going to be NH4. That's it acting as a base. It's accepted that H+, so we're going to have a H+ there. And ammonium carboxylate salt. So this is going to look like something like this. So that's our ammonium carboxylate salt. So now to get rid of this, we just have to heat it. And this is then giving it the loss of H2O. And that's going to form NH2. So we're going to lose 2 of these, and we're going to lose that. And it's going to remove the H2O, and it's going to form our amide. So the second way we can form an amide is by heating a carboxylic acid with an ammonium salt, so like we had above, with urea. at 120 degrees C. That is how you can produce. Slightly simpler way, but you have to use this. And it smells. We can then transform our amide, if we really wanted to, back into a nitrile. I hope you wouldn't do them in the same reaction. Seems a bit counterproductive. But you can produce a nitrile from this by dehydrating it. It's a dehydration reaction with an amide with P4O10. And this will form nitrile. So we're going to, for example, I'll do this molecule. Heat P4O10. And that's going to form our nitrile. So as we can see here, we went from 1, 2, 3 propanamide to propanitrile. So now we're going to look at the formation of a nitrile. So we can only do this from an aliphatic halogen alkane, so something like we all know what a halogen alkane looks like, base, that would be a chloroalkane, basic. So we can't do this in aromatic due to the stability of it, but all you have to do to form nitrile from an aliphatic aliphatic halogen alkane is by reacting it with KCN. And of course, this is the whole, like the alcohol, nucleophilic substitution. Due to the polarity in this will be attracted to this will push the electrons towards there, and then we get the business of we form that, and it will increase the chain length by 1, and it will form our Cl minus. That's a nice one. So you got to heat it and reflux it for that reaction, and that is the gist of that. So now we'll move on to the formation of an acid chloride. So we looked at acid chlorides before. So we can look at it as a derivative again of a carboxylic acid. So we want to go from our carboxylic acid to our acid chloride. So the way we can do this, we can have 3 reactants, and it must be carried out anhydrous because these acid chlorides are very reactive, as you saw before. And if you react this with water, we're then just going to form that again, and it's very counterproductive. So the 3 reactants we can use are SOCl2, which has got a funny name, which I won't even begin to pronounce. We're going to form, so I'm going to do we need to know a reaction, so I'm going to write down one reaction. I'm going to do ethanoic acid with our SOCl2. And this is going to form CH3COCl, ethanoyl chloride. So it's going to form SO2, which is the gas, and we'll see if that's important in a minute, and HCl, gas as well. The other 2 reactants we can use are PCl3 and PCl5. Now, SOCl2 is the better reactant because both products are in gases. These 2 will form solids, maybe, or liquids. They'll form in the same state as the product we want. So the ethanoyl chloride in this way would be easily extracted because all the other products are in gaseous state. So now we want to look at the hydrolysis of an amide and a nitrile. Sorry if I'm moving a bit fast here. Hydrolysis of an amide and a nitrile. So the hydrolysis of a nitrile, all it uses is a H2SO4 catalyst and water, of course. This is a process of going from here to form our carboxylic acid. Sorry, I didn't know if I said that correctly before, but a nitrile to a carboxylic acid. But we're going to look at the hydrolysis of amides and nitriles. So that's the hydrolysis of a nitrile. So in this, the nitrogen group in the cyanide is actually converted to ammonium, and the acid will react with the ammonium. In this case, nitrogen-containing product is ammonium sulfate. So that's what this catalyst would react with. Or we can carry out this reaction in alkaline conditions, and this is when we heat the nitrile under reflux with an alkali. So we're going to use NaOH, a strong base for this. And this will give a carboxylate ion, however. So C N hydrolysis in OH minus conditions. But this is going to form our carboxylate ion. However, all we got to do is to fix this is react it with a strong acid, so to reprotonate the solution to give our carboxylic acid, so HCl, which was able to donate that H and form the alcohol group there. We could do the hydrolysis. Now we're going to move on to the hydrolysis of an amide. So we need to heat the amide under reflux. So amide, we know it to be like this. So we want to heat it. It's H2O as well. With NaOH, so it's done in alkaline conditions. This will give a carboxylate ion again, which we have to then reproton it. So now we're going to look at the reduction of nitriles. So if you want to reduce an aromatic nitrile, such as that is horrendous, phenyl nitrile, like this, we have to use a strong reducing agent again, something like LiAlH4, and of course we need to dissolve this in ethoxyethane, and this is just going to produce, I'm not drawing the calculus structure, will produce our amine. So to recover this product, it is water soluble, so it will dissolve in water, the H. And the two layers, you're going to form two layers. You're going to form an organic layer, an organic product, and an inorganic layer. So if you look in a solution, you'll have maybe a layer of organic on top, and then your layer of inorganic down here. And of course, if it's the other way around or like that, you can just distill it off. You'll use a separating funnel. But when it's not water soluble, amines are basic, so you add HCl, and this will cause neutralization, so your salt will be formed, which will be water soluble, and then you add water, two layers will form again, and you'll have a separating funnel again to separate them out. So in that case, you'd have your mixture going on. But because your amines are basic, because it's NH2, you've got these two. You can just do a simple neutralization reaction, add some HCl, in it goes, and you'll form your salt. And then you separate and funnel it out. And there you go. There's your product. So that is unit 4.5 of carboxylic acids and their derivatives. Bit of a longer episode. And we've covered quite a lot there, if you're taking notes. So thank you for watching.